So let's continue. Let's talk about the structure of matter. What is matter? Well, matter is the stuff that everything is made out of. So the question is, what is the smallest piece? Right, if I had a piece of paper and I were to tear it up, and then I took that half of it and tore it in half, I tore that in half, eventually I get to really small stuff. And ancient Greeks reasoned that there must be a smallest piece. So Greek atomos means not sliceable. So an atom then is the smallest amount of matter that we have. Well, we thought that was true. We start with molecules. It's the smallest division that is identifiable as a certain substance. And of course, molecules are made out of atoms that correspond to elements. Well, as we started probing this in 1911, we discovered the nucleus. So it was now the smallest thing. And so nucleus of the atom was very dense. It contained protons, which were heavy particles that were positively charged. It also had something we called neutrons that did not have a charge, but had about the same mass of a proton. And then it also had electrons that orbited around the nucleus. They were negatively charged, they were light, they're a fundamental particle, have no structure, but we built these things called supercolliders, and we took, say, protons, and we accelerated them up to very high speeds, and we smashed them into each other and discovered that it was no longer the smallest thing because the protons would break into pieces, and we called those pieces quarks. So protons and neutrons are made up of these quarks. There's 6 flavors of quarks. There's up, there's the down quark, there's the top quark, there's the bottom quark, and there's the strange quark and the charm quark. So if we were to look at, say, a piece of gold, something that maybe we'd all like to have right now, a piece of gold we know consists of gold atoms. Now if we look at those atoms, at the center of each atom is a nucleus. And if we were to look at that nucleus carefully, we'd see that inside were protons and neutrons. And if we were to take one of those protons and break it up, we'd see that it's composed of quarks. A proton consists of 2 up quarks and a down quark, where a neutron would be 2 down quarks and an up quark. So dimension is a physical nature of a quantity. And dimensional analysis is something we're going to do to look at the dimensions of equations, of different values that we calculate. So different dimensions, length, for example, is a dimension. It's the physical nature of a quantity. If I say I've got 3 of something, it doesn't really tell me the physical nature of it, but if I have 3 meters, it tells me the dimension. Or if I have 3 square meters, it tells me I'm dealing with an area, or 3 cubic meters, a volume. Velocity would be in meters per second, so its length over time is its dimension. An acceleration we measure in meters per second squared, so its dimension would be length over time squared. Dimensional analysis is a technique to check the correctness of an equation, or to remember an equation we can't quite figure out whether things are squared or if there's a velocity there, there's no velocity there. So the dimensions of length, mass, time, and different combinations can all be treated as algebraic quantities. We can add them, we can subtract them, multiply, divide, but we know that both sides of an equation must have the same dimensions. Now, dimensional analysis can't give us numerical factors. It's a limitation of trying to remember equations. But it also does allow us to check calculations which can show up in the units. So for example, if I know that I'm calculating velocity and I keep track of my units everywhere, and in the end I get meters per second squared, I know I've made a mistake somewhere. And so dimensional analysis allows me to check my calculations, make sure I haven't made a mistake if I keep track of all the units. So let's look at an example. Consider the equation x equals 1/2 at squared, where x is the length, a is acceleration, and t is time. So the question we ask is, does this have the correct dimensions on both sides? So we start with the left-hand side, x. Well, x is a length, so the dimensions of the left-hand side of this equation is length. All right, and on the right-hand side, the 1/2 we can ignore, because it's dimensionless. Numbers are dimensionless. Acceleration is length over time squared. And time, of course, is the dimension of time, and we square it. So we can treat these, like I said, as algebraic quantities. And if we do that, we have a t squared on the bottom and t squared on the top. We cancel those out. We see that on the right-hand side of the equation, we have the dimension length, which is the same as the left-hand side. So the equation x equals 1/2 at squared is dimensionally correct. Well, how about the equation velocity is equal to at cubed, where v is velocity, a is acceleration again, and t is time? Does it have the correct dimensions? Right, so on the left-hand side of the equation, velocity is length over time. The right-hand side, acceleration is length over time squared. And t cubed would be time cubed. And if I cancel those out, I have t cubed on the top, t squared on the bottom. That leaves me with 1 time, so that's length times time. So we see here that this equation is not dimensionally correct. We have length over time on the left-hand side and length times time on the right-hand side. So let's do another example. If we know acceleration is proportional to some power of velocity, and if an object is moving in a circle at the radius r, find the powers if the proportionality constant is dimensionless. All right, so we know that acceleration is proportional to v to some power and radius to some power. So we'll call these powers v to the nth power. We don't know what n is yet, and the radius of the circle r will be to some nth power. Now let's plug in our dimensions. So acceleration is length over time squared. K, again, we said is dimensionless. We can ignore it. Velocity is length over time, and we raise that to the nth power. And length, radius is a length, so we raise that to the nth power. So now we compare these sides. Well, let's multiply this out first. We see that we have length raised to the n plus nth power when we multiply them out, and t is raised to the minus n power. So now we can compare those. We see that n plus m, the power of length on the right-hand side, has got to equal the power of length on the left-hand side, which is 1. And on the right-hand side, we have t to the minus n power, and on the left-hand side, we have t to the minus 2 power. So we know that minus n has to equal minus 2. So then it's pretty easy to solve for n and m. N is equal to 2, and plug that in, we get m equals minus 1. So now we throw that into our equation. We see acceleration is proportional to v squared over r. The next thing I want to talk about is about uncertainty. There's uncertainty in every measurement. And this uncertainty carries over through all the calculations. So we need a technique to account for this uncertainty. We're going to use the rules for significant figures to approximate the uncertainty in results of calculations. So what is a significant figure? A significant figure is a reliably known digit. And all non-zero digits are significant. Zeros are special. Zeros are not significant when they're only being used to locate the decimal point. Now, if we can write all of our numbers in scientific notation to indicate the numbers of significant figures, it removes all that ambiguity when the possibility of misinterpretation is present. So we'll try to write all of our answers in scientific notation if possible. So how do we do operations with significant figures? Whenever I multiply or divide 2 or more quantities, the number of significant figures in the final result is the same as the number of significant figures in the least accurate of the factors being combined. Least accurate means just the one that has the lowest number of significant figures. When I add or subtract, we round the result to the smallest number of decimal places of any term in the sum or the difference. So for example, how big is a room that measures 12.71 by 3.46 meters? Well, 12.71 times 3.46, if I just plug it in my calculator, for example, is 43.9766. Well, that's way more significant figures than I had before. right? We can only have 3 significant figures because 3.46 only has 3 significant figures. So therefore, the answer must be rounded to 3 significant digits, or the area is 44.0 square meters. Let's talk about rounding. Calculators generally report many more digits than are significant. So you need to be sure when you report something that you properly round your results. We can get slight discrepancies introduced by both the rounding process and the algebraic order in which the steps are carried out. They're to be expected. They're not a problem in the problem-solving process. However, if we're doing experimental work, we need to use a more rigorous method and to ensure that we have the correct number of significant figures in whatever we report out. So, stop the video here, and I want you to practice these concepts and then come back for our final video of the day.